Toplanan ve geri dönüştürülen plastik ambalajlar yepyeni ürünlere dönüşerek hem ekonomiye katkı sağlıyor hem çevreyi koruyor. PAGEV, plastik sektörünün birleştirici gücü. Toplanan ve geri dönüştürülen plastik ambalajlar yepyeni ürünlere dönüşerek hem ekonomiye katkı sağlıyor hem çevreyi koruyor. PAGEV, plastik sektörünün birleştirici gücü.
But another thing that is very important in composites is the length of the fiber. So as the fiber length goes higher, the properties will also increase. And of course, the properties will approach to an asymptotic value, a final value, where you would obtain the maximum possible improvement when you have continuous fibers. So when you have woven fibers, when you have tows, when you have continuous filaments, you have the best results. Okay? When you have chopped fibers, then your properties are reduced. And as the length goes down, your properties will go down as well. So if you really want to benefit from the properties of the fiber you are using, you try to use the fibers as long as possible. But of course, sometimes, depending on the part geometry, it is not possible to use very long fibers. If you are doing injection molding, you have the extruder and you have the mold. So as you go through the process, your fiber length will become smaller and smaller. Even if you try to use a longer fiber to start with, you put it in your pallet and the hopper, but the extruder will essentially degrade and reduce the length of the fiber. So depending on, and 20, 30 years ago, people looked at a lot of extruder design to minimize the degradation of the fiber length. Okay, so that's another thing that you need to know if you are doing injection molding. In injection molding, of course, you have sharp corners and thin cavities, geometrically complicated parts. So you will not have really long fibers. But people are trying to, even these days, there's ongoing research in the US, how to use long fibers in injection molded parts. So that's an ongoing research. In compression molding, and we will talk about it a little bit later, the fiber length is a little bit longer in compression molding. Okay? So, but still, we are talking about maybe 1-2 centimeter long. In injection molding, the fiber length is maybe 200 microns, so 0.2 millimeter. Okay? And the fiber length, fiber diameter is 15 microns. So your fiber aspect ratio is another important property for discontinuous fibers. Fiber aspect ratio might be around 30 to 50 to 80. Okay? So that's also an important property, fiber aspect ratio. Okay. Fiber orientation is, of course, very important. We talked about this is the stiffness. I mentioned the equation to determine the stiffness of the longitudinal and the transverse. But this is the strength. For the strength of this composite, if you test it along the fibers, it is almost 400 megapascal. And then it very rapidly goes down. And for the transverse strength, it goes down to 50 megapascal. So you see, if you have a little bit misalignment, your strength will go down from 380 to below maybe 300. So there's a big drop if you are not perfectly aligned. So you will hardly ever get the maximum benefit from the alignment in the final product you are really using. So most people account for these off alignment in their design. In the transverse direction, the properties are very poor because when you apply a tensile stress, you are essentially pulling apart the resin. the fibers will not really help you a whole lot when you have that. So in making laminates, going back to F16 structure, wing structure, F16s, the first prepregs with the carbon fiber, they were unidirectional prepregs. So the fibers are all in the same direction. To make the part, you have to stack up these layers in such a way that you rotate the fiber orientation layer by layer, right? So you might have, you know, the top and the bottom 0 degrees, and then the second layer and the one from the bottom maybe 30 degrees, 45 degrees, and 90 degrees. So there is a layup sequence or so-called stacking sequence, which is important in laminated composites. So many of the earlier designs spend a lot of time in determining the stacking sequence, best stacking sequence for that particular application. Of course, later on, people decided to develop woven fiber prepregs. So then designs became a little bit more relaxed, because when you have a different weave, you have certain amount of fibers going this way, and you can determine the amount of fibers going that way. So you can have, for example, 70% of the fibers aligned this way and the 30% aligned that way. So you can, you would have more flexibility in the design and also in the processing when you have woven fabric prepregs. Yeah, these are some of the pictures of different types of commercial fibers. You can buy this woven. This is like a plain weave. You can buy unidirectional tape. You can buy a rowing. And so these are filaments. This is basically all rowing. You can buy these. Depending on the process, you can then feed this into a chopping gun. If you are doing it with a spray, for example, you can just chop these fibers on a surface and spray with the polymer and produce the component that way. This is random mat, glass random. This is woven fabric. These are all glass fibers. And these fabrics have very nice drapability. So you can put it in a mold. It is easy to handle. You need to be careful with the edges. See these toes can come off really easily. So when you are handling, you have to kind of, and when you are cutting, you have to, you know, cut nicely and pay some attention so that the edges are not deformed. But otherwise, it is fairly easy. The random mat also, if you are making processing with random mat, you buy the big roll, and maybe the length of the roll is like 1 meter, and it is like 100 meter long or 60 meter long, the mat. Because of the nature of the microstructure, see, you will see some gaps, right? Because so both at the micro scale and the macro scale, there is some non-uniformity in these random mats. So you kind of need to make sure that as you are using your roll, the one that you purchase, at every 10 meters, you need to kind of cut maybe a little part of your fabric or random mat and weigh it and see if there is any variation in the amount of fiber per unit area. And you might have 10–20% variations. So you might be designing the part to have 16 layer and the fiber content maybe 50 grams, and then you decided that, well, okay, I'm going to cut this big and 16 layers. But then you might have 20% variation in the weight, which will give you quite a bit variation in the fiber volume fraction, so your properties will be non-uniform from component to component. Okay, so you need to be a little bit careful, but there is nothing that is too bad when you are working with random matte fabrics. This is yeah, so these are now some, this is carbon fiber. I think this was Cytec carbon fiber, or maybe it's a hexal. The typical diameter of this is like 8 micron, and for glass fibers, 12 to 14 micron in diameter. More recent carbon fibers, IM series, 4 5 micron. 8 micron is much thinner than your hair. You can see it, right? So when you have a toe, many fibers, you probably, if you have good vision, you can pick a single fiber, and you can see it with your naked eye. 8 micron. 4 micron, you still can do it, but it becomes difficult. So, but when you are testing these fibers and looking at, you really need to work with the microscope. Single fiber tests possible, by the way. I mean, I show you the stress strain diagram for a single fiber linear elastic behavior. Yes, it is possible to run a test on one single fiber. So you have to kind of have a frame. If you are interested in, I can tell you a little bit about testing single fibers. But these are the SEM images. So you have a fracture surface like this. You will have the, and one thing is this is very, very nicely circular. The diameter of 8 micron is very uniform. It really will not change. 8 micron, 8.1, 8.0. The diameter is very nice. These fibers are very circular. The cross section is very nice, circular. If you look at this, this is 5,000 magnification. You will start seeing some surface texture. So there are some streaks like these coming from the production. And if you really zoom in at higher magnification on these fibers, you will have some sub-micron surface texture. These kinds of streaks is visible on these fibers. Now, depending on the fiber, you will have a sizing on the surface, so-called sizing. And this sizing is usually less than 1 micron thick. You will not be easily see it under SEM, but the surface is a very thin layer of coating. Usually, this layer is to create a improved interface with the resin. Okay? So you will have a nice bonding, chemical bonding, covalent bonding with the maybe epoxy. So these sizings on the surface are usually, companies do not really disclose the chemistry, but these are silane-based sizings, and there is some literature on that. You can get rid of this sizing by heat treatment. If you heat it up to carbon fibers or glass fibers to 400-500 degrees C, you will essentially desize the fabric, and you can apply your own sizing. And I mean, if you are in the polymer chemistry and the surface chemistry, you there's a whole group of people dealing with the surface chemistry of fibers and the sizing formulations. And that's very important in the interfacial properties, okay? Because that's how your stress or the load is transferred from within the composite, between the fiber and the resin. This is another fracture surface of glass. I think these are glass epoxy. You see a lot of fracturing. You see fiber surfaces. When you look at the fracture surface, you would like to see a lot of fracture, which indicates that these bands indicates that, or these, there has been fairly reasonable interfacial properties. You would like to see resin on the surface of the fibers. You really do not want these kinds of clean gaps or the large holes in the resin that the fiber just came out, pulled out cleanly. If the fiber is like pulled out, and in the fracture surface you see a bunch of holes in the resin, it means that you do not have good interfacial properties. You do not have good interfacial bonding. So if you make a composite part, break it, look under the microscope, and in one side you have a bunch of fibers, in the other side you have a bunch of holes in the resin, your composite is not good. You will not really get benefit from the presence of fibers. So you have to deal with the sizing and the surface chemistry. All right, so carbon, this is a tow, this is Kevlar, yellow in color. It is highly impact resistance, high impact toughness. You can process the Kevlar fabric, you can buy it. The same way you process glass or carbon fabric. It handles very similarly. It is very soft. It is very easy to drape. You can mold it, handle. You can have coarse weave. This is a kind of a coarse weave. You can have very fine fabric like silk, very nice, fine. So you can get Kevlar in different form, and you can make your composite. All right. So fibers. What do we have? We have glass. We have carbon. We have Kevlar. We have also quartz fibers, and quartz fibers are used for their electrical properties, dielectrical properties, and used in radomes. And what is a radome? Radome is the cover of a radar. So you have radar, you have the antenna, you transmit the electromagnetic wave, and so you have the nose, for example. The aircraft, they have noses. Inside you have the antenna and the radar, right? So you have to cover that. Now, you want electromagnetic or the radar wave to travel without absorption, so you really cannot use electrically conductive material on the radome, so it has to be quartz is the one, and there are certain resins that are used in radar applications. If you are interested, you will not see a whole lot of literature on radar, by the way. I mean, you will find literature in radar, but not the composite literature. People, they don't publish these kinds of things. Radar absorption. For example, yeah.
Is this going to be relevant for this smart cars as well, because they will use a lot of radar?
Possibly, yeah. They use. It depends on these autonomous vehicles. What kind of detection technique they use? They use cameras. They use sound. And they use high frequency waves. So these are competing technologies. I don't know. I think the successful solution will use a combination of these methods. But yeah, this is definitely a growth area, an upcoming area. All right. So yeah. Okay. So let me talk a little bit about the nano clay or a clay as a reinforcing agent. This is a layered, nano clay is a layered silica-based material. It has been around for centuries. The use of clay in polymers started maybe in the first in nylon. I think used in Toyota research labs showed that the nylon and clay really improves a lot of properties. In I forgot the exact date, but maybe 20 plus years ago. And since then, people really started using clay. Especially the polymer community started looking into clay. Not so much the composites industry. The composites industry with the fibers, they already improve the properties a lot. The appeal of clay is cheap, right? So you can get clay and you may use a small amount of clay. Now, for fibers, you really need to use at least 20% by volume. And for high performance applications, 65% by volume in the laminate fiber side. Clay, you can use 2%, 3%, 5%, and people primarily stayed in that range. And people didn't really exceed 5% clay. There are a lot of studies claiming successful integration of clay and improving properties with 1.5% clay, 2% clay. But the reason why this is called nano clay is because these are layered structures, silica sheets, and the thickness of each sheet is a few nanometers. So you have essentially 1 nanometer sheet. This is one single flake, let's say, and then you have an interlayer distance, and then you have another one. So this is called interlayer, but since this is kind of at the nanometer scale, especially for thermoplastics, this research started with thermoplastics, the macromolecules will not be able to penetrate in this spacing. So what people have done is people basically formally change the surface chemistry of this silica clay and try to separate the spacing. So, and those materials are called organoclays. Okay, and you can buy maybe half a dozen or a dozen different types of organoclays with different basal spacing, and they verify it using X-ray diffraction, so that you can essentially determine what the spacing is. So the whole idea is to separate these layers from each other so that you can essentially have the polymer diffuse into this. And it is called exfoliation. Exfoliation, it is difficult to achieve, but once you exfoliate these, it means that you separated these clay sheets or platelets on its own, and you get improvement. So this is, well, maybe this is not clear. I will later show you some other ones. But you would like to increase the strength, decrease permeability, definitely improve flame resistance, and improve water resistance. But if you really are not sure in the processing, you can essentially reduce all these processes. I mean, you can end up reducing the strength. There are lots of studies that show that the strength of the polymer with the addition of clay essentially went down. So it is very important how you process the clay. Now, there are some commercial applications. Beverage containers, because of the improved barrier properties, you can have, for example, beer barrels. Is very important that you really, because beer, you only buy it in glass, right? You do not have it in others. So you really need to have a good barrier property for the bottle. So there are some trends. Tennis balls use some sort of clay, I think some bouncing properties. These are for wear resistance. This is an engine cover for improved thermal stability. There is a step for wear property. There is some clay content. So there are some commercial products coming up. So the processing ways, there is melt mixing, solution blending, and in situ polymerization. But primarily, you have the molten polymer, you have the nano clay, and melt mixing, you apply shear. So there is shear, and usually you have, high shear. So you really have different blending methods and the shearing methods. So if you have, if you can apply high shear, you kind of disperse the clay better. Of course, it depends on the viscosity of your polymer and so on. Solution blending, essentially you have a solvent, so you dilute the polymer, so the polymer is less viscous, then it is easier to mix, right? And then you have the solvent, you can either, I mean, you need to get rid of the solvent in one way or another. Sometimes people use different types of alcohols and acetone and so on, but these are kind of more at the research level. People are kind of trying. In situ polymerization is another way to add clay. Another way that is very common is sonication. If you look at the literature last 10 years, there would be several hundred articles that use sonication. Sonication, you essentially have either a bath sonicator. Bath sonicators are commonly used in labs to clean things, right? So you put the resin, liquid resin, maybe thermosetting, epoxy type with the clay, and sonicate. You either use tip sonicator with a sonicator probe, so you dip it in, and maybe 1 minute, maybe 10 minutes, sonication, so the reports range from 1 minute to 60 minutes. But we looked at the results. After 5 to 10 minutes, the effect of, I mean, you achieve most of the dispersion within the first 10 minutes. Okay? So there's another way, commonly used way, tip sonication. You have to be careful with the temperature of the resin, though. You have to do it maybe in an ice bath or a cold water bath, so you have to cool, because if you continuously sonicate with a tip sonicator, the temperature of the resin will go up. You really do not want to, heat up your resin early on. All right, so this is your clay platelets like this. The polymer, so if you only do like that, this is a micro composite. This is not good. See, the platelets are not separated. Your polymer molecules have not really diffused in. This is a little bit better. They are kind of separated, these platelets. It's called intercalated nanocomposite, so you'll get some benefit. And this is the ideal case, so-called the exfoliated. So the terms that people use, intercalation and exfoliation. Those are the two things. If it is exfoliated, it means that you basically have these nice individual platelets separated from each other and blended with the polymer. Of course, in reality, you really do not have an ideal nanostructure like any one of these. It's a mixture. Usually it is a mixture. And people, what they do is you observe these things under TEM. SEM will not really show you whether you have intercalation or exfoliation, but using TEM, transmission electron microscope, you need to section these very thin and look at the platelet. But that's a very small area, and maybe 1-2 sample. You really do not know how the whole entire part or the product is. Very likely, you will have a combination of an exfoliated regions, some intercalated, and a lot of microclusters. And if you have these microclusters now, how big they are? Maybe they are 5 micron, 10 micron, 20 micron. It can be as large as 50 micron. Then you are not really getting any benefit from these regions where you have exfoliation. I mean, your big clusters, clay clusters, will govern the behavior. They will be essentially accumulate the stress. They will absorb moisture. They will give you everything that you do not need. And then you will say, well, it doesn't work for us, right? So it is kind of difficult to get rid of these large clusters. I will show you a few. This is a this is like around 10 micron cluster. You see these stacks of clay. This is in epoxy, and this whole thing, let's see, this is maybe around 10 micron, is smaller than one single glass fiber. The diameter of glass fiber will be greater than. So if you look at that, that's a very small microscale additive, but nevertheless, you really want to get rid of all these clusters. It is not clear to me, and I'm not sure what but you might have also some nanoscale submicron voids or trapped air. And we have some evidence in some other studies that these are also trapped air inside the cluster. So what do they do? Well, you know, I'm not sure, but that is not really something you want, these kinds of submicron trapped voids in the part. So there are some maybe examples of these trapped air. These are clusters. By the way, this is 1 micron. Now we have smaller submicron clay dispersed in. This is 500 nanometers, so you see maybe this is 500 nanometer, maybe if you, so you have smaller. If you use a higher magnification, you will see individual platelets. So you see there are like, this is 25 nanometer, and then you'll see there is maybe 10 or so clay platelets separated by about 1 micron. So the whole idea is to separate them and all that. Okay? So that is what this nano clay is all about. Okay, so now I will talk about autoclave cure. What is, I mentioned about autoclave cure a little bit. So the whole idea is this. Prepreg, this is the prepreg, this is how you buy, this is the material you use, this is the protective sheet, you have to peel it. This is how you store it. If you are working with a prepreg, make sure that you know its shelf life. You make sure that you store it in a sealed bag, in refrigerator, and as dry environment as possible. Because if it is, and as you open and close the bag, if you open and take it out, there will be, you know, moisture. So if you, wherever you are processing this, try to reduce the moisture, because the resin will absorb moisture, and when you are curing, if you do not vent or get rid of this moisture properly, you will have defects. You will have voids that will reduce the properties by 10, 20, or 30%. Okay? So this is our raw material. This is what you buy. This is the autoclave, and there are different sizes. I mean, the autoclaves are pressurized ovens, and then you make laminates, and this it goes through the curing process. So at the end, we will have a laminated composite. Fiber volume fraction of this, you would like to be around 60–65%. This is pretty much the highest fiber volume fraction you get. It is higher than injection molding. It is higher than compression molding. It is higher than vacuum infusion. It is higher than resin transfer molding. Okay? The highest, very likely, the fiber content you'll get will be in these, using these prepregs and using an autoclave. Now, I will tell you the pressure and the temperature range. Okay? The pressure range in autoclaves, many composite parts would be processed under 100 psi. Okay, what is, those of you who are not familiar with psi, around 15 psi is 1 atmosphere, so we are talking about 5, 6, 7 atmosphere, kilopascal. So 600 kilopascal, 500, 600 kilopascal, and so on. Many prepregs are processed 60 psi, so 400 kilopascal, more or less, round numbers. But there is a range, so the pressures are not very high. The pressures, injection molding, you have much higher pressures, right? However, the sizes are much large. Therefore, if you have 400 kilopascal and if you have like 2 meter diameter with an area, your forces would be extremely high. You will have very high forces on the autoclave. So that's why these autoclaves are expensive and they have very thick shells, and you have to be careful with the pressurization of large autoclave and the chamber. So these are the parts you make, aircraft components, automotive. These are wind turbine blade. Again, that's an aircraft component, a wing skin. You can build ribs and spars, and so you can do this part in one cure cycle. Prepreg is pre-impregnated sheet. This is a B stage resin and the fiber reinforcement. A stage, B stage, C stage. B stage is a little bit cured. It is sticky. So it is sticky at room temperature because you really do not want the resin to flow away from the fabric. So it is solid-like. Okay? That is why this is what is called as B stage. Okay? Now, the prepreg is supposed to be, good quality, so you will not have voids. You have a very nice uniform fiber volume content, uniform fiber volume fiber distribution. You can get it as a unidirectional sheet and tape or fabric. These days, a fabric is much more common, but you can get these unidirectional. But you have to be careful in handling these unidirectional tapes. These are, carbon fibers like this. All fibers are in this direction. You get your tape, you cut, you hold it, you peel it, but it is very easy for this to separate. Okay? There's not a whole lot holding these fibers in this direction. So if you, bend it or whatever, you don't handle it right, it is also during layup, the unidirectional. I personally don't like working with unidirectional in the lab. We mostly use woven fabric. I included this for reference for you to see what the major suppliers are, and you have the copies, Tenkata or Tenkate. This is a major supplier of prepreg material. Some of the prepregs, they are expensive, but you have to wait for, after you place the order, 3 months. You have to wait for 6 months. Then if you have an order for a roll, 100 yards, they will tell you, okay, we will fill your order 6 months later. It is very likely because that same method is used for military purposes, so some country, whether they are essentially have an ongoing supply and the company really doesn't want to change their production for your order. There are some you can get it, it is in stock, but there are some that it is very difficult to obtain. But you can, essentially, some of these are used in B52, B2, B1. Those are commercial, readily available. They do not publicly disclose what prepreg they are using, but one of these. Hexcel is another one. This is a US company, Cytec also. These are the major suppliers of prepregs. There are maybe a few more, but I personally find pretty much everything I need using Cytec, Hexcel, and this Tenkate. Drape, conformability tack, that is the thickness, debulking. These are the important prepreg properties. If you are making a thick laminate, you need to debulk, you need to compact, heat a little bit so that you build, so you prevent wrinkles. You build the laminate step by step. Once you lay it up, you will do a vacuum bag. This is, depending on the product, you can do hand layup, You can manually cut it from the roll, put it on top, or you can use automatic tape laying or automatic fiber placement machines. And I think some, I don't know, Corsa might have some of these machines. So there are a few of these. Tai probably have some of these tape laying machines and so on. But traditionally hand layup, and these are relatively, expensive machines, but hand layup is also quite frequently used. But you have to have a very clean room. You have to have a positive pressure in the room so that there is, continuous airflow. So handling prepreg for commercial applications, you have to have the right people and trained people to handle the prepreg, because it has to be, nicely stored. There's an expiration date. If it is not stored, if the bag is left open longer than it is supposed to be, you get moisture and your prepreg. By looking at that, the prepreg, you'll not know the difference, but the properties would be 20% less.
Moisture nasıl etkiliyor property'leri?
Well, okay, so the moisture, you might have relative humidity here or any, 50%, 60%. It doesn't have to be too humid. When you leave the prepreg, the resin, it is the B stage, it will absorb moisture from the ambient, right? And it is very little. If you weigh it, it will be maybe 1–2% of the weight. So you can detect it. You need to have a right analytical balance to know that it is gaining moisture, but it is a very small amount. When you make a laminate with the prepreg that contains moisture, the water is expelled during cure, okay? But it may not leave the laminate, so it may essentially leave micro voids. So your void content will be much higher in the final laminate. Now, we have not really talked about voids, but there's another group of people, maybe in the world, 24. They are all they do is void, and we have done a lot of studies in formation of voids, because voids in thermosetting resins is the primary defect that creates lower performance. So in aerospace, high quality composites, your void content should need to be less than 1%. Less than 2% might be acceptable. You would like to have less than 1%. So you cut your part, look under the microscope. At 200 magnification, you may see 1 or 2 small voids. That might be okay. But if you see several voids, then your part will be inferior. Now, you might say, well, I have like 2% or 5% voids. What are their effects? Well, 1,000 megapascal flexural strength will go down to 700. 600 megapascal may go down to 300. So anywhere from 50% to 30% reduction because of 5–10% voids. So the void is a big deal in composites, especially in thermosetting in laminates. And many people do not really understand or appreciate this. They never cut their sample, they never looked at our product under the microscope, and they have a bunch of voids. Okay, let me show you a little bit. Okay, this shows how to prepare the layup. So you are drawing on the prepreg. This is the prepreg. So you need to have the right scissor to cut the carbon fibers. So you are taking the protective sheet. It has to be cold so that you kind of grab and peel it off. If it waits at room temperature, it becomes sticky. It is difficult to grab on and peel it. So there is some experience required. But it's, yeah, so this is the vacuum bag. That's the vacuum port there. The white is breather so that this vacuum is distributed. Yeah, I think it has two, and this is the tacky tape. This he's putting around. The bag will be on it, so it will be sealed. I think he will do debulking first. This is the cowl plate, again to distribute. It also gives you a better surface texture. It distributes the force and the pressure. Thermocouple is placed. That is kind of how you check the temperature. Breather, it absorbs the excess resin. The Prepreg, when you heat it up during cure, it becomes viscous and all right, so the vacuum bag. So you check, you make sure that it is not leaking. So he's checking the tape, making sure that there is no leak around. Because if it leaks, then you lost several $1,000s. I mean, these parts are expensive. You may have multiple, okay, so it is inside the autoclave. This is the metal plate, bottom is the tool plate, and he will hook up the vacuum and the thermocouples to the inside autoclave, and then he will, you know, the cure cycle will start. This is another one. Okay, hold on. Tool plate, usually metal. This doesn't have to be metal. It can be a composite mold or tool plate. The tooling can be composite as well. This is a simple. So he's trying to, yeah, he's peeling the protective sheet. Always use gloves. You can use latex gloves. Yeah, this is again bleeder or breather cloth to absorb excess resin. Vacuum port. Okay. So there are a lot of consumables. I mean, all these you use and you throw it away. So this is an expensive process, time-consuming, labor-intensive, and you have to have the right person. He's cutting the vacuum bag, and he will have these quick connects. He will just snap the vacuum port. Yeah, this is the autoclave door. And there are different ways, mechanisms to open and close. You really want to open and close the door quickly. The vacuum port is hooked. There is a vacuum pump outside. He's closing and locking the door, and the cure cycle will start. Yeah, so this is a really big one. So you can easily walk inside this autoclave. This is for production of some 787 component. There are some stories that people walked in and then they closed the door, and so there are some accidents like that, and that doesn't happen often, but there is some. You have to be kind of careful. There will be many tool plates and instrumentation inside, and it's a big area. The heating, usually it could be gas or electrical heating, and the temperature is controlled through multiple thermocouples. You have to control the temperature and the pressure. This is how the Autoclave Works. Here you have this heating unit. You have a fan. Here you have a motor. That fan essentially circulates the gas. You can use air, but an inert gas is recommended. Nitrogen, sometimes a lot of. This is a large area interior, so pressurizing this takes some time. Heating that also takes some time. I mean, think about in your homes, you have ovens, and to bring it to a certain temperature, it takes 5 minutes, right? Or 10 minutes. So these autoclaves, of course, they are heated up very slowly. It might take 30 minutes or 60 minutes to bring it to the maximum temperature. So there is an interior workspace and the outside tubular shell, the surface, and this is insulated, so the air flow comes in and it is circulated inside while the curing takes place. This is the process of the layup. You have seen this. Assemble the vacuum bag, and then the vacuum, so it has to be sealed. You can put thermocouples. And the whole thing with autoclave is the pressure, right? You can make the same part, same tool plate, and do it in oven. Much cheaper equipment. One can be $1 million, the other is like, 10,000. So can you make the part without applying the pressure? Yes. You can essentially follow the same temperature profile without the pressure, and you will have a part. The part you made in the oven will be thicker, a little bit thicker, 25% thicker. Why? Because of not having pressure, resin is not pressurized and it didn't really flow out. The only thing that makes the resin flow out in oven cure is the vacuum pressure, right? So vacuum pressure, depending on the vacuum pump you use, it will be around 1 atmosphere. It will be around, let's say, 15 psi, 100 kilopascal or 90 kilopascal. That vacuum pressure will essentially pull some resin out during cure. Those layers will be consolidated, will be compacted because of the vacuum pressure. So you will get, let's say, 2 millimeter thick composite laminate. Same tool plate, you put it in autoclave, you cure it at, again, you have 100 kilopascal or 90 kilopascal vacuum pressure, but on top of that, autoclave is pressurized to 200 or 300 kilopascal. So you have essentially on top of the vacuum pressure, 3 times as much pressure applied to your laminate during cure. As you heat it up, resin starts melting. So with that added pressure, you will have, let's say, much better consolidation. These layers will get close to each other, right? And then your laminate at the end will come out to be, instead of 2 millimeter, it will be 1.75 millimeter. Okay? So what did you change? You changed the fiber content of the laminate, right? So instead of having 50% fiber volume fraction that you would get in the oven, you get 65% fiber volume fraction, or even more. So as a result, your properties will be much higher. So your properties will be 30% higher because of the increased fiber content you get in an autoclave. So that's the whole deal about using autoclaves. Having that extra few atmospheric pressure applied on the part, compact the laminate, and increase the fiber content. There is also another benefit of this applied pressure. If you have voids or air trapped inside, it compacts the voids. Therefore, instead of having 4% void volume fraction, you will end up having 1% voids. Voids will be much smaller in general. Average void size will be smaller. And some of the voids will be collapsed and diffused into the part, so they will essentially disappear. Now, also, as you apply pressure, as the resin flow takes place, some of those voids will move out with the resin as well. So, added pressure essentially gives you increased fiber volume fraction and reduced void content. And therefore, you really need autoclaves for high quality composite laminates used in high performance applications. This is what I said the motor is. The fan is kind of course you have to insulate these. This is your heater, so the gas is heated and this fan circulates this, and you can have multiple thermocouples to monitor the temperature of your part, and you have to come up with a strategy or a software. This is usually done with a software to control the temperature and the pressure. Vacuum is usually kept throughout the cure cycle in the bag, so it's always under vacuum, and then you ramp up the temperature and the pressure, you hold it 3-4 hours, and then you cool it down. Now, this cure cycle, it's called cure cycle. Time, temperature, variation of temperature and pressure inside the autoclave. It's a cure cycle. People spend a lot of time to optimize the cure cycle. Why do we need to optimize? By the way, where do we get the cure cycle? Who tells us the cure cycle? Wherever you are buying the Prepreg, that Hexcel and Cytec and Tenkata, those companies, sell you the material, and then they tell you the cure cycle. They tell you for this material, you need to have a ramp rate for temperature 4 Fahrenheit to non-Fahrenheit for 60 minutes, bring it to this temperature, keep it 3 hours, and cool it down at this rate, and apply 60 psi pressure. So you buy the material, you know the cure cycle. This is to make things easy, right? But in reality, you can try to optimize if you know what you are doing, if you really want to advance and do a little bit better. The right cure cycle depends on the size of the product and the thickness of the laminate. So how do we optimize a cure cycle? We would like to finish the cure as soon as possible to reduce the cycle time, to make the part. Instead of 6 hours, we would like to heat the autoclave, maybe finish it in 5 hours, 4 hours. But depending on the thickness of the part, as I mentioned earlier, you might not be able to, number one, heat the autoclave that fast, but assuming that you heat it up, your part, if it is thick enough, the heat will be generated and you will have a temperature overshoot, and then essentially you will burn your part. So that's why you have to make sure that you have the thermocouples. And by the way, in this environment, in the production environment, thermocouples frequently fail, and you will not get a reading, or you will get a lot of variations, and if you really have done this. So it is always a good practice to have multiple thermocouples, and then one thermocouple will give you the autoclave temperature, so that follows the cure cycle, okay? And then other thermocouples will be on the part or next to the part, and so you will have a group of thermocouples that gives you the temperature of different parts of the autoclave. And the autoclave, although you would like to have a uniform temperature, it really is not uniform. There might be a few well, 5-10 degree variation within the autoclave. So it depends on where you put your part, you may not follow. So there will be some leading thermocouples, some lagging thermocouples, right? So you have to have some sort of software to tell you how to, because depending on the thermocouple, you will say, heat it up, don't heat it up. Heat it up, don't heat it up. Okay? So let's see if we can. This door opens, there's a hydraulic mechanism to open and close. He's hooking up the thermocouples. These are the access ports inside the autoclave, so you might have, you know, 10 or 12 thermocouple ports that you can hook up. The vacuum, connect the vacuum source. The placement of the vacuum port is important. You need to do the leak test. Of course, this having the, for example, if when you are buying an autoclave, having this easy open and close, another $30,000. If you don't pay for that money, what you have, I mean, see, this is very nicely, it closes and all that. If you don't want to pay that money, you'll have a bunch of bolts all around with nuts this big. Maybe you have 12 bolts like, you know, this diameter, so you have to kind of, it takes, I mean, we didn't pay money for the hydraulic for our autoclave. It used to take my students to do it, you know, 30 minutes just to open and close the door, 30 minutes. Because there are several bolts, they are very thick, so you have to be safe and so on. Okay, consolidation is important. Vacuum, amount of vacuum is important. Heat up rate, dwell temperature, temperature tolerances, cure time, and cooling rates. These are the design, cure cycle, process parameters. Okay. If you are interested in this, you kind of study the relationship between these parameters and then design your cure cycle and make sure that you follow your cure cycle. Any questions about this? I will go into wet layup, WARTM and RTM. These are the molding methods, but molding mostly for continuous fiber reinforced. Or for random mat. So wet layup, vacuum-assisted resin transfer molding, and RTM, resin transfer molding. Some of this information we also obtained. I would like to acknowledge a textbook or a book. Research monograph written by Suresh Advani and Murat Sözer. Professor Sözer is a faculty member at Koç University. So when he was doing his PhD in US, he has written a very nice book on manufacturing of composite materials. That's another book that I recommend about composites fabrication. So We are kind of dividing this into two. Short fiber reinforced composites, injection, compression, extrusion, and then advanced composites, mostly continuous fiber. Remember, the properties very much dependent on the fiber length. So if you have continuous fibers, wet layup, WARTM, RTM, autoclave, filament winding, pultrusion, those let's call advanced. And sometimes people call if the fiber is carbon, it is advanced composites. If it is glass, it is not. But you know, it really depends on you what you call advanced. To me, anything you do is advanced. I mean, you don't want to say I'm not doing anything advanced, right? So mechanical properties for short fibers, we are higher than the polymer, but not extremely high. Degree of complexity, high. Once you know the process, it is not very complicated. At least the tooling is not complicated, but the properties would be 1 or 2 orders of magnitude higher. All right, so this is some of the geometric complexity you get from the injection molded parts. Some resin transfer molded parts would give you some shape complexity with the ribs and three-dimensional structures. But again, the wall thickness, I think in injection molding, it is usually 3 millimeters or less. Again, 3 millimeters or less in composites would be applicable. So these are the 3 processes we are talking about. Wet layup. Wet layup can be in a vacuum bag or not. Okay? If it is, you are essentially wetting the fabric with a hand roller, and you let it cure. This vacuum infusion, here the fabric is dry, you are infusing and impregnating the porous media with a resin. This is your resin bath. And then here with RTM, you have a closed mold. You have a top and the bottom mold, matching molds, you are closing it. The difference between RTM and WARTM is this is a closed mold, this is one-sided mold. The resin is injected under pressure. So since you are injecting under pressure, you can impregnate a denser or a lower permeability fabric. So the fiber volume fraction here will be higher. Okay? So you can essentially put a lot of fiber into the mold and inject under pressure. Here, the pressure is only vacuum pressure because of the vacuum bag, all right? And so the fill time is important because the filling only takes place because of the vacuum. So it is pulling the liquid resin. So viscosity becomes more important, extremely important. But why then do we have WARTM and not do RTM all the time? Well, if we have large parts, right, you cannot really, for wind turbine blades, you really cannot do 60-meter long mold, right? So for large parts, you use WARTM. For low cost, if you are doing 4 or 5, for boats, for yachts, for structures, you use WARTM. So it is very cost effective. I think I talked about this. Random, we talked about different weaves. By the way, the plain weave, 5 harness and 8 harness, you have different weave patterns. So as I said, you can manipulate the anisotropy. You have different, you might have different amount of fibers in one direction and another. Also, by having these kinds of patterns, different weave structure, you can drape or you can shape these fabrics slightly better. So depending on how you drape and what the shape complexity is, you can select different weave patterns. That's a whole another thing that you may want to look into if you are doing those kinds of processes. This is hand layup. Lay down 1 coat of resin on the mold, dry fiber, you wet the fiber, another layer, so you go layer by layer, and then you brush You apply the roller with the squeegee, get rid of the voids if you can. For wet layup, low cost of raw materials, minimal tooling, easy to manufacture, you can really make large parts. Labor intensive, vapor emission, so you have volatiles, or there's another thing. So when you are using different kinds of resins that are volatile, so the place has to be properly ventilated, depending on your, so you have to have protective gear given to the worker. So you have to be careful with the volatiles and the vapor emissions. And of course, the low consolidation pressure. Now, if you are not using vacuum bag on the hand layup, there is no pressure really. You are not applying pressure. All pressure is you apply by hand. And that is, by hand, you can apply, I mean, much less than the atmospheric pressure. So by a roller, whatever the weight, maybe it is, if you really want numbers, I would give you, you can apply per square inch a few pounds, a few kilograms, so you do 20% of the atmospheric pressure with your hand. So that will not get rid of voids. So your product will not be really good quality if you do a hand layup. There will be voids, high void content. I would guess that you will have 5% or higher voids, maybe 10%, 12%, and your fiber volume fraction will be 20%, 25% with hand layup. 25. Autoclave, remember, 65%. There's a big difference, 25 to 65. Now, vacuum bagging, of course, you now have, that's a relatively easy process. It takes some time to get used to it. The tool plate, you have in the video seen the parts of it. You have this preform. This is your composite laminate. You put a cowl plate to apply the uniform pressure or give a better surface texture. Then you have a perforated release film. This one, when you have around the cowl plate, you don't have to use the cowl plate, by the way, but if you do, around from the edges, resin will be removed. The resin, the liquid resin will be moved around the edges, and then it will flow through these pores and then into the bleeder. So that fabric, it was white color. It is like a cam yünü gibi bir şey yani. Tamam öyle. It will absorb the resin and your excess resin will go there. Make sure that you use enough bleeder here so that the resin will not get into your vacuum port. Okay? If you do not, then this vacuum will pull the resin and then it will cure inside your vacuum port. So you have to kind of clean it. You have to burn it and you do things, or you have to, dissolve it in acid and all sorts of problems. Okay? So that's the function of the breather or bleeder. And then the vacuum bag, you have to seal it all around. You have seen it in the video, especially if you have thermocouples going in. The thermocouple needs to go through the sealant. So you need to make sure that you tap it and make sure that there is no leakage. So thermocouples and things going in inside the vacuum bag is always a potential area for leakage. Now, at room temperature, everything may look good. So if this is an autoclave, you put an autoclave, you cook it. At high temperature, these sealant tapes become soft. They kind of give their rigidity a little bit. So at room temperature, you can do your leak check, and it might be just fine, but at higher temperature, you might have leaks. So you kind of need to pay attention to sealing properly. This, again, high void content, low fiber volume fraction. With the vacuum bagging, with wet layup, from 25% fiber volume fraction, you go to maybe 28, or you go to 30, 32, that range. You will not get to 55. Okay, this is a video from my lab. Resin and cure agent is mixed. Degas, if you are mixing with a mechanical mixer, make sure that you degas it. Because in the mixing, you have air bubbles mixed in, so you need to get rid of the air bubbles. We were doing heated wet layup, so these are the heating elements at the bottom of the tool plate. This is a Teflon sheet so that we easily remove the part we cured from the tool plate so that it doesn't stick on the metal. So the vacuum port is there. Wet layup, a little bit of resin. Of course, this is mixed with the cure agent now. So once you mix with cure agent, the time starts ticking. You have a gel time, 1 hour, so you have to finish the process. These are my students doing the illustration. So yeah, we applied vacuum and we used the vacuum regulator to make sure that we are consistent among experiments. So that's a 93 kilopascal vacuum level, but you really don't need to in a production environment. You have a vacuum pump, whatever, you know, it gives you, you have a good pump and you don't need to regulate the vacuum level usually for this hand layup processes. All right, so at the end, so when you make that part, you see these dark areas. These are the resin pulled out from the wetted fabric as a result of the vacuum. So those are coming from the porous perforated peel ply absorbed by, because we have a cowl plate right here, the laminate here, and around this, the resin is pulled out to improve the consolidation. But again, this is a limited thing. You can use this technique for reinforcement of silo, industrial silo, for example, infrastructure, for bridges, for concrete, for improvement for earthquake reinforcement and things like that. There is, I think Mini Cooper has a part here, and then this is another example of a boat hull. Now, liquid composite molding, LCM, here the impregnation is not done by hand. The impregnation, the wetting of the fabric is done by the vacuum. Okay? Under this, the Wartum Now we have flow-through porous media. RTM is the injection under high pressure. Thermoplastics, by the way, are not really used in these kinds of processes because of their high viscosity in general. However, people really are trying to develop thermoplastic resins that give you nearly as good properties as epoxies. And I think there are some new products out there, the thermoplastics. The thing is, you can recycle. You can recycle thermoplastics, and people are actively trying to get, move away from thermosets for high volume applications. For if you are making it for an aircraft, well, you have only thousands of it. It really doesn't matter whether you are recycling or not. But if you are making automotive or if you are using other things, if you have millions of it, you would like to recycle it, right? If you have limited use. Now, aircraft B-52s, they will use it for 100 years. They will, recycle, repair. I mentioned you the radome. The B-52 radome is this big, the nose of the aircraft, right? And it's a 60-year-old component. And every 5 years, they uninstall that part, they check it, and then they repair it. So in a given component, you would see at least a dozen. Well, maybe 10, maybe, but the ones that I have seen at least have a dozen patches, repair sections. Okay? So thermosets, composites, you have to try to repair if it's a high value product. All right, so I am here saying that the resin is very important, has to be less than 500 centipoise, less than glycerin. We talked about that. You have to choose the wetting properties, the cure kinetics. You need to also look at the thermal expansion coefficient. There are some candidates, cyanide ester and bismillamide. These are really nice, and they are used in certain applications, high performance applications, missiles and rockets and things like that, bismillamide, BMI, high temperature applications. Okay, in Wartum, you have this vacuum line, vacuum pump. It pulls, once the bag is in place, you pull the vacuum. You have this resin inside this bag. You can have a regulator. So this is kind of impregnating the wind turbine blade, and flow slowly progresses through the part. A peel ply is a highly permeable fabric, and you can have these peel plies right here and here, so that you basically enable resin to reach the composite part, but when the part is cured, you essentially pull it apart from the part. It's called peel ply. On top, you can use distribution medium, and here, or distribution media, this one here. You would have this resin inlet, and then you really want not a really small point, but you want the incoming resin to spread and then infuse and wet the fabric relatively fast. So you use so-called distribution media to distribute the resin early on. Okay? It's a low, it's like a mesh, low, high permeability. It has a high permeability, and it makes the resin go fast. All right, so resin comes in, and then you close the inlet and you let the part cure. So this is the distribution media, so that the flow progresses in a uniform way. Right. Okay, so resin is going to come through here. It's coming. It is wetting. So ray tracing or tracking, see this you want to avoid wetting very fast here. Otherwise it will kind of fast go like this and reach the exit and you'll have dry spots. So the shape of the fluid front is kind of important. And there are software, by the way, to simulate these kinds of filling. So of course, this is in a vacuum bag, your fabric is inside. You are now, it slows down, the impregnation slows down. Initially it is fast, but now you need to overcome the viscosity. See, the resin now reached, but still impregnation continues. This is your vacuum pump. This is the resin trap. You can check the vacuum level here. And I think the whole part is wetted. And we are clamping the inlet and then clamp the exit and let the part cure. So this is pretty much the basic Wharton process, vacuum-assisted resin transfer molding. You will have multiple inlets when you are doing the wind turbine blade. You have multiple flow channels and all that. And the distribution media might be on top so that the flow is distributed faster. And yeah, these are some of the examples. Marine structures, energy, aerospace defense. This cargo door is also made by Wharton. So see, for example, cargo door, it's not really structural, right? I mean, so you really do not need autoclave. Okay. Disadvantages, resin, you are limited with your resin choice, labor dependent, long fill time, low consolidation pressure. This is essentially a scrimp process. You put the distribution media on top. See, this now is to reduce the cycle time. So the filling is much faster. Resin goes like this and then comes down to impregnate. It's called the scrimp. That's a version of Wharton. There is some pressurized Wharton we developed. We use magnets to apply consolidation pressure, but in general, you can, of course, make the Wharton and then put it in a press or an autoclave, but again, you are significantly increasing the cost. If you take the Wharton layup and put it in an autoclave or press under the hydraulic press. But if the shape is a little bit complex, this would be difficult. You need to have a die. We have tried magnets to apply the pressure. So you essentially, if you have a magnetic plate, you can generate 100 psi with the magnets. Right? You have those magnetic lifts that you can lift steel plates in the machine shops, right? Those are either electromagnets. For used cars, before they scrap it, they lift the car with the electromagnet, right? Or in metalworking. So those magnetic lifts essentially rated based on the force they generate. But for composites, you can look at their cross-sectional area and divide the force by area, and you can calculate the pressure they can apply. And it happens that with those kinds of magnets, you can apply enough pressure to consolidate it, right? Provided that you have a magnetic plate at the bottom. So you have this pressure, and then you need to have a lubricant between the magnet and the vacuum bag, and then slide it on the surface, right? So you are essentially ironing, ütülüyorsunuz yani, değil mi? The layup. But that iron, ütü is çok kaldıramıyorsunuz yani onu. Tabii bir ton, 2 ton ama iyi bir lubricant koyarsanız onu slide edebiliyorsunuz ve you apply really nice consolidation pressure without needing the autoclave or without needing the press. So this is a process we developed and we published several papers. This is a new idea that we find out. Resin transfer molding. I think we will wrap it up in 5 minutes. It's a closed mold. You place the preform, inject the resin, cure the resin, and then open and take the part out. Aircraft, helmets, these are even bathroom fixtures and parts of the automotive industry uses RTM. Let's do one quick video on this. So binder application is to prepare the fabric. So you basically would like to apply some kind of binder to the fiber so that once you place multiple layers on top of each other, you have one nice shape to put in the mold. So it's a binder. Preform preparation, so you have your preform here. You would prepare, you cut it to the size, you stack them, you put them on top of each other depending on the thickness of the part you are making. There is a binder so that they don't slide against each other. You then take these and put them in some sort of press to warm them up. Apply some sort of compaction pressure, but this is just to give it the shape of the, you are not introducing, you are not wetting, you just bend it, heat it up a little bit. The layers have mechanical contact, you press the fabric against each other, the layers, therefore they come out in one single piece, and then you essentially stiffen. It becomes not too stiff but easy to handle. Then you take these parts to the mold where you inject the resin. So you have the pump. This is a combination of vacuum and an injection. So you pull vacuum and then you essentially inject under pressure, and you end up. Yep, so the resin is coming in. Of course, this is inside the mold, right? So this is a, all right, it's going up. And then this is a closed mold. All right. So vacuum is stopped. When you see the resin is coming out from the exit, and you let the part cure. And the part is demolded. This is RTM. So you can do, since this is a closed mold, you really cannot do very large parts. But medium-sized parts, you know, this size, yeah, if you are doing very high production rates, you can afford to build the mold for RTM. So time savings compared to wet layup and Wharton, because you are injecting much faster under pressure. You get good surface finish. Yeah, one of the advantages of RTM is since it's a matching mold, both sides against the metal, you get really good surface finish. You get fairly, depending on the mold design, complex structures, but higher tooling cost, longer cycle times, and so on. People are using high-pressure resin transfer molding. Some automotive companies are using so-called high-pressure resin transfer molding, applying quite a bit. By the way, yeah, this is a time, years versus blade length. So initially, this is the wind turbine blade length years and the manufacturing processes. So initially, wet layup, some resin transfer molding here, injection molding, but see these are really small blades. And then most recently, you have Wartum. So all these large blades last 10 years because of the cost and the ability to make large parts. Almost all wind turbine blades are made by Wartum, vacuum-assisted resin transfer molding. These are some comparisons: wet layup, fiber volume fraction, Wartum 58, strength is 171, and for Wartum 225, impact strength and 72 to 93 kilojoules per meter square. So these are the difference between wet layup and Wartum. Defects, you have to be careful with the defects. Micro voids, some flow or race tracking, the edges, because if you do not cut or place your fabric properly, the resin will move very fast around the edges, along the edges, and then reach the vent. So you will have weak spots, you will have dry spots, you have micro void formation, and these are the defects. So at this point, I'm not sure if you're interested in the modeling, but the flow through porous media is how we do this. This is the permeability, and there are all sorts of flow problems. This is no inertia forces, and you basically ignore or get rid of acceleration terms. Yeah, these are some of, if you are interested in modeling. The primary, if you are interested in the modeling, I included this slide, but you go to Loos and Springer. Springer is retired now. Al Loos is about to be retired. He's in his 60s. Loos was his Springer's PhD student, published this consolidation model in '83. Gutowski was a professor, he's also retired at MIT. He published some consolidation model, '87. Lee and Tucker recently retired some. So if you are interested in flow modeling and consolidation and effect of pressure flow through porous media, you go back to '80s. And Springer also did the cure cycle, autoclave curing and all that. So they wrote a book on smart autoclave. It's a thin book. You can see all the modeling in that book, the heat transfer and the resin flow, consolidation, everything. So George Springer. So those are the primary contributors early on to this field. For fiber orientation, Chuck Tucker did in '80s some publications. So orienting short fibers in molded composites. So these are the important names. So I kind of put them in here, process simulation. And yeah, this is the book I mentioned, Murat Sözer and Suresh Advani. These are one of our publications here, and Loos and Springer, and so on. Okay, so I will stop here. We are not able to cover some of the components. I would have needed another 30 minutes, but I don't have 30 minutes, so I apologize for that. So I will be here today, the next week. You have my email. It is very easy. altan@ou.edu. You can find me. My life stories on the web. I mean, these days you can get anything and everything about anyone on the web. So you can you can reach me through email. So I would be very happy to answer your questions if you have any. So thank you.
Thank you. Evet, hocamıza bir teşekkür etmek istiyoruz.
Oo, ne güzel.
Bugünün hatırası olarak şöyle alalım hocam sizi.
O peki, tamam. Fotoğraf.
Çok keyifli bir sunumdu. Gerçi 2 ayrı salonumuz olduğu için biraz orada biraz burada ikisini de kaçırmak istemiyoruz.
Evet. Devam edecek 2 gün zaten. Bugün
evet,
öğleden sonra.
Yarın da devam edecek. Sonrasında da PPS devam edecek.
PPS tabii.
Sizin şahsınızda hem PPS organizasyonuna çok teşekkür ediyoruz.
Ben teşekkür
hem de
ederim.
size sizin için yorucu olan, bizim için çok keyifli olan bu sunum için teşekkür ediyoruz.
Ben
çok
teşekkür ederim.
Buyurun.
Bakışlarınızı alabilir miyim?
Çok
Teşekkür
ederiz
ederim.
hocam.
Tekrar teşekkürler.
Sağ olun.
Evet, herkese iyi günler diliyorum. Sağ olun. Evet, teşekkürler.